Hello students, welcome back. We completed section 1. Now let's go to section 2, linear congruence. More precisely speaking, what we are studying is linear congruence equations. Kind of like this. Ax is equal to c, or equivalently speaking, ax plus b is equal to 0, except that instead of equality, we use congruence modulo m. Same here. But congruence already includes the term equivalence because congruence is already an equivalence relation. So if I rewrite it as a linear modular equivalence equation, come on, that's too redundant. What do you mean by equivalence equation? For that reason, and also for simplicity, many people, including our textbook author, takes abbreviated version and call all those linear congruence. Still, you have to remember this is an equation we are working on, so we have to solve for x. Moreover, we are doing number theory, so everything here is an integer. A, B, C, and even m, all integers, and also x. The solution must be integer solution. Now, does it ring a bell? Integer coefficient equations with integer solution? Yes, you should. It's the Diophantine equation we are talking about. We went through that in lesson 3. And are those linear congruence or linear congruence equations intimately related to the Diophantine equation, more precisely speaking, linear Diophantine equations? The answer is yes. Indeed, look at the conclusion. It goes hand in hand with the conclusion for linear Diophantine equation. A and c are integers, they are arbitrary. D and m are positive integers. M is arbitrary, D is not. D is determined by the GCD of A and M. Now, if the GCD divides C, then we have infinite many solutions. If the GCD does not divide C, then no solution. That was the conclusion for linear Diophantine equation, right? Moreover, infinite many solutions, maybe, yeah, but we had specific format. We were able to get all those in lesson 3. And if you're unsure about any of those, please go back to lesson notebook, lesson 3, and then re-study that. Here, very similar thing is going on, except that we are working on congruences, so having infinite many solutions and walking away is not sufficient. Among those infinite many solutions, let us reclassify those in terms of equivalence classes, modular congruence, and it turns out precisely the incongruent solutions. So there are many infinite many solutions, but if you classify those in terms of equivalence relation modulo m, then there are only the distinct equivalence classes of solutions. Moreover, we have this form, which is very similar to the conclusions for the Diophantine equation, linear Diophantine equation, except that we have this modular form. This x0 is of course the same x0 for the GCD in Bezout's linear combination expression. And then one more thing, the incongruent solution, yes, m over d times r, and r runs from 0 to d. 0, 1, 2, 3 after d minus 1. We are doing modulo m, so in general there are m equivalence classes, 0, 1, 2, 3, and so on for m minus 1, but not all of them qualify, only d of them. That's striking, and that d happens to be the same as this GCD. And everything fits. It's a beautiful result. As for the proof, yeah, it really goes hand in hand with linear Diophantine equation. You see, AX is congruent to C. What do you mean by that? AX is congruent to C. By definition, this is the same as the left-hand side minus right-hand side is divisible by M. So this is AX minus C is divisible by M. So this is some quotient times M. Okay, and then we can re-express this like this. Flip this Km to the other side and C to the other side. We have AX minus Km is equal to C, where K is a quotient. But instead of writing like this, it's going to be more convenient to do it this way. AX minus MK is equal to C. Excuse me, it should not be equality. Oh, yeah, it's equality. It's right, excuse me. This is modulo M. This is modulo M, but I use this Km. So from this point on, everything is equality, and we have the Diophantine equation. And the reason I changed this Km into Mk like this is because, wait a minute, that was not really necessary. I could have started from Mk and then got all these directly. Okay, that looks better. A and M and C are given, and then X is unknown, and we have to solve it. K is also unknown, but that solution may be a part of this linear Diophantine equation, but it's not really a part of this congruence equation because the solution that we are looking for is X. So does it mean this K plays no role? Well, it does a little bit. We'll see. So here we have two unknown variables, X and then K. X is more important one, and K is a little less important one. And we have a solution form for linear Diophantine equation. Let's see. If the GCD of AMM does not divide C, then there's no solution. If that divides C, then there are infinite many solutions. And then those infinite many solutions have specific form. Okay, let me show you finally. Oh, by the way, before starting, yeah, okay. Instead of AX minus MK, okay, all right. This may be more convenient. And then rewrite this negative K as Y. Okay, all right, let's do that. Okay, all right. Red, blue, okay, all right. Look at this linear Diophantine equation. That's what we're going to study from this point on, all right? Okay, this thing is hidden. And then, from what we did from lesson 3, we can write the solution like this. First, find the linear combination expression for GCD. You can do that through Euclidean algorithm. We went through those in lesson 3. AX0 plus AX0 plus MI0 equals to D form. And then for arbitrary integer t, we can write the general solution like this. C over dx0 plus m over dt. That's x. And then y is c over dy0 minus a over dt. But y part is not that important. X part is really, really important. And y part did its work finding out this x0 thingy. So let's focus on the x part. And then we must work out the congruence too. So to this, let's apply the division algorithm to t. And then plug in and do your computation. Voila, that's what you're going to get. So t is qt plus r by the division algorithm, which I just highlighted in purple. This one t, purple. And then if I break up this parenthesis, d and d cancel out, I get this md, which I just highlighted in brown. And then c over dx0, m over dr, they stay, and then both c and m are divisible by d, so these fractions are actually integers. And finally, md is congruent to 0 modulo m. So that drops out. Voila, we have our conclusion. C over dx0 plus m over dr. So that concludes the proof. Not only we prove this conclusion, no solution and d incongruent solutions, but as a matter of fact, we found a specific formula to find this d incongruent classes of solutions. Like this. How do you find this x naught? Ax naught plus my naught is d. So that's x0 and y0. Bezout's linear combination expression. And remember how to get that. We can use Euclidean algorithm to get that. And then x0 goes here. C over d, that's an integer. M over d, that's an integer too. And r goes from 0 to d. And why does it go from 0 to d? Greater than or equal to 0, less than d? That's because we reduce arbitrary t through the division algorithm. Oh, by the way, besides the proof, we have a remark here. What is it? Oh, yes. This theorem here and the general solution is written in the general form, but it's not the most convenient form. The most convenient form is after simplifying to the lowest terms. Here's an example. 15x is congruent to 25 modulo 10. Instead of working those out directly and to the formula, yeah, you can do that, but nobody will actually do that, I think. Just simplify to the lowest term. 3x is congruent to 5, and then 3 and 10 are relatively prime. So d is 1, so you don't really have to worry about dividing by anything. So put directly over here, d is 1, so it's easy computation. And of course, getting this Bezout's linear combination expression, that's going to take a bit of an effort through Euclidean algorithm, but you can do that. Now, how about the next example here? 15x is congruent to 25. That part is the same, but this time let's consider modulo 12. Division by 5, we have 3x is congruent to 5, the same as before, but, big but, what's the GCD? The GCD of 3 and 12 is 3, and 3 does not divide 5. So there's no solution, and you can walk away. So simplify first, and then apply this. So 99% of the time, nearly 100% of the time, you can reduce this denominator d into 1 after simplification. So this may look like complicated, but in fact it's much simpler than that. No time for any other thing, just a proof. So let's stop here and let's resume in the next video.